Now, let's study the Davisson-Germer experiment. So this is the experiment that allows us to prove the wave properties of particle. So the Davisson-Germer experiment consists of a piece of nickel crystal. So this piece of board over here, it's not a board, it's actually a piece of nickel crystal. Okay, so what you're going to have here, you're going to have a thick filament over here, some filament over here, and you're going to heat up this filament over here. So when you heat up this filament over here, what will happen is this filament will undergo thermionic emission. Okay, thermionic emission says that if you heat up something, especially metal, it will emit electron. Okay, it emits electron. So electron is going to escape from this tube over here, from this opening over here. So electron is going to come out from here due to thermionic emission. So now there's electrons coming out, represented in this spreading out kind of beam. So there's electron coming out from here. So what we're going to do, we are going to place a kind of setup right in front of the opening over here. So this setup here is connected to a circuit over here, and you have something like a rheostat over here, which you can control the resistance. So by controlling the resistance over here, you are able to adjust how much potential difference you want to apply across these two electrodes over here. So this is one electrode, this is another electrode. You have the right hand side, the right hand electrode over here to be the positive electrode because it's connected to the positive terminal, whereas the left electrode over here is connected to be the negative electrode. So this is a negative electrode, this is the positive electrode. Then in between these two electrodes, there's going to be a potential difference because you're applying across a potential difference, which is VB minus VA. So I believe this is B, this is A lah. Okay, so right now, because there's a potential difference in between these two electrodes, there's an electric field that is going to be formed in between these two electrodes. So this purple arrows here is representing an electric field, and it's going to point away from the positive electrode, and it's going to point towards the negative electrodes. So you know that electrons are negatively charged, so they will undergo they'll experience a Coulomb force which is in the opposite direction of the electric field. This is what we learned from electrostatics, that chapter. So that for a negative charge, the force experienced by the negative charge is in the opposite direction of the electric field. So since the electric field is pointing to the left, we know that this electron will be experiencing a force to the right. And because the electrons is experiencing a force to the right, these electrons will be pushed to the right. And if the electrons are being pushed, we understand that these electrons will be accelerated to the right. So you can see that the electrons are accelerated by the electrodes and directed at the crystal. So this setup over here, this pair of electrodes here, serve to speed up the electron when it comes out from the opening. You speed up the electrons, then you direct the electrons, which are moving now at a higher speed, towards this nickel crystal over here. Okay, so to understand why is it being sped up, why is it being sped up, you can think of it. This is a positive electrode, right? So electron is negatively charged. So of course, negative and positive, they will attract each other. So you think that this electron will get attracted towards this positive electrode over here. But you just pass through this electrode with a higher speed right now, aiming towards the nickel crystal that we have over here. Okay, so once it aims towards the nickel crystal over here, what happened is we are going to the electron to strike a nickel crystal. That's what I mentioned just now. Then now what I'm going to do is we are going to place some kind of detector. Okay, so some kind of detector, it can be a photomultiplier tube or it can be a sensor. Okay, in now this generation maybe a sensor, but in those times I think it's maybe a photomultiplier tube. Okay, but don't worry too much about the device, just know that it is a detector. So we are going to install a detector that can measure from 0 degree to 90 degree to see where can we find the scattered electron. Because electrons will hit onto this nickel crystal, right? So it will somehow get diverted into another direction, or it somehow get reflected, or somehow it will behave not the same because it hits on the crystal. So this detector is here to try to detect where is the scattered electron, or where does electron deflected off to. Okay, so this detector here is able to move across this 180 degree semicircle over here to try and look for where is the electron where does the electron get deflected to, or where is the scattered electron. So this detector can be moved to detect the scattered electrons at any angle theta. So we can label this as angle theta. So if you place your detector right in front over here, so that is angle 0. And if you push it to be tangential to the plane over here, to the nickel crystal over here, that is 90 degree. So normal over here is 0 degree, here will be 90 degree. Okay, so right now, because you are able to adjust your detector from 0 degree to 90 degree, you are able to plot a graph of 0 to 90 degree, and you can try to determine what is the intensity of the electron that is being detected. If there's no electron being detected, then the intensity will be 0. If there's a lot of electrons being detected, then the intensity is high. So you are going to measure across a range of 0 to 90 degree, from 0 to 90 degree, to try to look for where is the place where you see many scattered electrons, or where do you see most of the electrons go to. Okay, so we're going to set here 0 degree and 90 degree, and we are going to start measuring it. Okay, so this is the diagram this is the same setup, but if you look at it from a top view, I would say, we look at it from above. So if you look at it from above, this is where we have the filament, and we apply a voltage over it to heat up the filament. So once you heat up a filament, once again, there's the mining emissions, so electrons will be coming out from this filament over here. Then it's directed through this accelerating anode over here. So you have your positive and negative over here applied through this circuit over here in order to speed up the electron when it emits from here. Okay. In this case, they set the circuit like this. They set this part over here to be the negative, this part over here to be the negative electrode, this part over here to be the positive electrode. So negative, positive, so the electron will get attracted. So you move into this tube over here, then you exit from here in the form of electron beam. So basically there's electron coming out from here at a very fast speed and hits towards the nickel target. So this is a nickel target, the crystal that we mentioned just now. Then we are going to apply, and we are going to have a movable detector. This detector allows us to measure the intensity of the electron that gets deflected off at different angle. From 0 degree to 90 degree, we can adjust our detector to see where does the electrons get scattered to. Okay, so this is a setup just being viewed from a top view. Okay, so when Davisson and Germer are conducting this experiment, what happened is the nickel target, because it is a pre-treated nickel, so it means that you're not doing anything to change properties of the nickel, it comes as its raw form. So at that situation, what happened is the nickel's crystalline lattice that we have over here are very irregular in terms of their arrangement. Okay, the lattice itself has some order to it. Okay, you can see there's order to the crystalline lattice of the nickel, but it consists of maybe you can call it as domains, but you can call it as regions where they are in different orientation. Okay, so this is the nickel target before it was being treated. So what happened here is the lattice arrangement are all in irregular orders at different regions. They are not nicely arranged. Okay, so since the nickel has a polycrystalline structure, so poly means that there's many crystalline structure, they are not arranged in an orderly manner. That's why we call it there's many crystalline structure. So we expect diffuse reflection to occur. So if you are Davisson and Germer, you try to predict what is the result of this experiment. So you think, if because this is nickel target and we know that the internal structure looks something like this, then probably we should expect that if there's deflection, right, the deflection will be there's reflection, right? The reflection will be very random because you do not hit onto where on the nickel target. So it might reflect off in various different directions. Okay, if you want to think about it, you can think of it as if this situation over here. We learned before in secondary school, if we have a very shiny surface, a very smooth surface, you have something called a specular reflection, in which you can have the angle of incidence equals to the angle of reflection, and they are both in the same plane. This is a standard one that we usually learn. But what happens today if our surface is rough is the reflected light will reflect off in all directions because of the irregular surface over here. So this kind of reflection we call it as diffuse reflection. And this is the kind of reflection that Davisson and Germer are predicting for the nickel target. Because they say that because inside the pot it's a polycrystalline structure, so it's very irregular. So it is as if it's similar to a rough surface. So if you're shining electron beam onto a rough surface, you should expect that electron will get scattered in all directions. Okay, so because Davisson-Germer are predicting that it will scatter off in all direction, they are expecting that at all angles from 0 to 90 degree, they should expect some amount of electrons being detected at all angles, because they say that it will get reflected off at all angles, right? So if you measure the intensity of electrons at all angles, you should pick up some electrons at all the angles over here. Just that there are no specific angle that you find a lot of electrons. There's no specific angle that you find little electrons. Every angle here will have some amount of electrons. So the kind of prediction that you have is that it's a diffuse reflection. So the graph will look something like this. At all angles, you find a non-zero intensity. Okay, there's some amount of electrons, but there's no particular place which there is a strong intensity of electrons. There's no particular place which it has a low intensity of electrons. The electrons get reflected off everywhere, so all angles will have a similar amount of electrons. So the intensity will be roughly the same across all angles. So this is what Davisson and Germer predict. Okay, and when they conduct the experiment, I think this is the kind of result that they get as well. Okay, but what happened afterwards is, okay, if we expect the electrons to behave like particles, we can predict the graph will look like this. Okay, so if we expect that they bounce off like balls, so they bounce off in all directions, right? So all directions we see a similar number of balls or similar numbers of electrons. Okay, but what happened is Davisson and Germer did something to the nickel target over here. What happened is it take this piece of nickel crystal over here, and he went to heat up the plate. Okay, he heat up the plate with the intention of removing the oxide layer on top of it. So oxide layer is something like rust, okay, but in this case this is nickel kind of oxide layer. So they intend to remove the oxide layer off on top of the nickel target. So I think they went and bake it. I'm not really sure what they do to it, but they put it in the very hot temperature, a very high temperature environment to remove the oxide layer. But I don't think it's their intention to it, but unintentionally, what happened is when they heat up the plate, the arrangement of the crystalline structure becomes more orderly. Okay, so you can see that previously it was a really random arrangement of all the crystalline structures, but after you heat up the nickel crystal, what happened is the lattice structures become much more regular. So you can see that all of them arranged in a similar orientation. So now all the crystalline structure become very regular. Okay, so when you have a regular kind of structure over here, you should expect that it changed from diffuse reflection to specular reflection, right? So you should expect that because it's something like a very smooth surface right now for the nickel target, what you might expect is if you shoot 100 electrons at normal incidence, you are shooting it at 0 degree, right? You're shooting it at the normal incidence. You should expect that all the electrons will reflect off in the same path back towards the left, right? If you're shining it to the right, you should expect that the electrons will get reflected off to the left, because it's a smooth surface. It's just like you shine light perpendicularly on the surface. You should expect that the reflected light will reflect off perpendicularly out from the surface as well, right? So you should expect that for this case, the electrons will be reflected off to the left. Okay, so so the kind of result that you might be expecting is at 0 degree, which is somewhere around here, you should expect a high intensity of electrons, because that's where most of the electrons get reflected off. Okay, and you move away, when you move towards 90 degree, you will see near none of the electrons gets over here. Okay, this is what you predict if right now it's a regular crystalline structure and it behaves like a specular reflection. So all the electrons will get reflected off in the same path, resulting in 0 degree to have a high intensity. This is what you should be predicting. Okay, but the problem is when they conduct the experiment, okay, the observation doesn't match the prediction. You predict that all the electrons will get reflected off at 0 degree. But the problem is the result that they get is something like this. This is the result that they get when they conduct this experiment, and when they apply a voltage of 54 volt over here, or across here, when they apply a voltage of 54 volt, they find that the angle in which you find the peak is around 50 degree. Okay, there's a drop in the intensity, then afterwards there's a rise in the intensity, then afterwards there's a drop in intensity, but it peaks around 50 degree. So somewhere around a random angle, which is somewhere around here, you find that suddenly many electrons get scattered off this particular path. Okay, whereas for the zero, which you previously predict many of the electrons will get reflected off, you see that there's nearly nothing get reflected off here. So definitely what you observe from the experiment doesn't match the prediction. So this is what happens with Davisson and Germer's. They were predicting that many of the electrons should be found around 0 degree, but it turns out that it appears at around 50 degree, which is something quite weird. Because why 50 degree? And why is it this particular angle? And why is it a drop, then a peak, then a drop? Why do you form a peak over here? So many things were unanswered at that time. It looks a bit weird, but this is the point where Davisson and Germer figured out that there might be something, they might have made some important discovery over here. Okay, well, yes, it is indeed an important discovery, because why do you find this peak over here? Is because this peak in the intensity of the scattered electrons is due to the constructive interference between electron waves scattered by different surface atoms. Okay, in other words, you find this peak over here is because of the constructive interference. So constructive interference is a wave properties, right? If you want interference, it's an overlapping of two or more waves, right? So they find this peak over here, which can only be explained by thinking that the electrons will undergo interference. So if the electrons did indeed undergo interference, that means that the electrons will have wave properties. So this is the kind of the thought process that they use in order to prove that electrons have wave properties. Okay, so the kind of result that they gave, the kind of result that they observed, prove that this is nothing related to specular reflection or diffuse reflection. This is not a simple reflection kind of experiment. In fact, what happens around here is similar to a diffraction pattern. If you remember from diffraction pattern, maybe a single slit problem, you can see that there's a very high central bright, followed by a dark, then there's alternating bright and dark fringes, something like that, right? So this is very similar to the kind of diffraction pattern that we see for the single slit experiment. So because it's similar to the diffraction pattern that we see, we can actually deduce that this is due to diffraction. This kind of graph can only be obtained if the electrons undergo diffraction. So if we manage to get this result, we are proving that electrons undergo diffraction. So if electrons undergo diffraction, we are proving that electrons have wave properties. Because only by having wave properties can something undergo interference or diffraction. Interference and diffraction can only happen because it's an overlapping of wave. So unless the electrons behave as wave, you're not able to get diffraction pattern. But now we see diffraction pattern, therefore we know that electrons did indeed behave as a wave. So we can prove that electrons do possess wave properties. Okay, so to sort of summarize the idea is that we were expecting that it is a normal kind of reflection in which it reflects back to the left. But what happened is through through Davisson and Germer's observation, the pattern of the scattered electrons seems to have a peak at a certain angle over here, and the kind of pattern that we observe over here is very similar to a diffraction pattern. So this is very similar to the diffraction pattern in which you have bright fringe, dark fringe, bright fringe, dark fringe, something like that. So because of that similarity, they say that if light undergoes diffraction and it looks something like this, so now we get something like this kind of pattern for electron. So we can say electron undergo diffraction. So because electron undergo diffraction, electron possess wave properties. So by doing that, Davisson and Germer actually proves de Broglie's hypothesis, in which de Broglie says that matter can also behave as wave. So now through this experiment, we are able to prove that electrons or any kind of matter actually do possess wave properties. Okay, so in the next video, we are going to figure out the relationship between this accelerating voltage over here and the angle over here. How do they all correlate with each other through mathematical manipulation of equations.